Hello, this is Mike Douglas and the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Piotr Nawrot, I think I got that right, of the University of Warsaw, who will tell us why hierarchical transformers are more efficient language models. And long list of collaborators on the slide, very interesting work. And so as I always do, I'll offer, you can ask questions during the talk, or you can put questions up in the chat, and I'll ask the question at an appropriate moment if you do that. And of course, there'll be time for questions at the end. So with that, Piotr, why don't we begin?
Thank you very much for the invitation and welcome everyone. My name is Piotr Nawrot, and today I will tell you about the model that we call Hourglass. And it's a joint work with my colleagues from the University of Warsaw and our mentors from Google Research and OpenAI. Quick overview. Hourglass is a transformer-based language model. And here I assume that you have heard about transformers already, as they have been used to quite a few tasks in the last years, and they yield impressive results. We don't use a transformer encoder or cross-attention in our work. You can think of Hourglass, that is our model, as a different implementation of transformer decoder. So that's that part in the red side, in the red circle. In this famous illustration of transformers. Our work builds on funnel transformer and units. The main difference between our model and funnel or unit is that our model is autoregressive, so it can be used for language modeling or image generation. Just a quick recap, a statistical model is autoregressive if it predicts future values based on past values. So for example, an autoregressive model might seek to predict a stock's future prices based on its past performance. And finally, I would like to share with you the main point of this presentation, our paper and Hourglass in general. Throughout the presentation, I will be trying to explain that further, but for now you have to trust me. And the main point is, and you could have guessed it by now, is that hierarchical transformers are more efficient language models. And I will try to start with some intuition behind hierarchy and building hierarchy. Then I will explain the model further. And finally, I will show you our results. So when I first started learning about neural nets and I was doing object recognition, I learned that to recognize an object, neural net decomposes a question into many sub-questions. And it's very similar to how human brain processes the information. Like in this example, that to recognize the human eye, a stack of convolutional layers firstly learns to spot all positions with eyebrows or eyelashes, and then combine the answers to tell if there is an eye somewhere in the picture or no. And it is, of course, a great simplification, as neural nets sometimes overfit the training set and pay attention to abstract features, some noise, but nevertheless, it constructs some hierarchy. And back then, I was like, okay, good job, neural net. It seems very smart. Then I was learning about transformers and how well they are able to encode the sequence for further use in transfer learning in some downstream task. And I read a paper in which authors postulated that it actually matters from which layer you will extract the representations, the embeddings, for further use in a downstream task. And for me, it was very unintuitive because I thought that the best embeddings are in the end, the ones that are produced by the final layer. However, they argued that the middle layers are a better choice as it's a point in transformer encoder where model accumulates the overall information about the whole input sequence, while the final layers are more focused on using this information extracted by previous layers to optimize the very specific objective, like prediction of the next token. And that's the quote from this paper, from the image GPT, the very famous one. So this behavior suggests that a transformer generative model operates in two phases, and that will be very helpful in the rest of the presentation and designing of Hourglass. In the first phase, each position gathers information from its surrounding context in order to build a contextualized image feature. And that's like high-level view at our input, at our image. And in the second phase, this contextualized feature is used to solve the conditional next pixel prediction task. And again, it was like nice neural net. So first you focus on individual tokens and local proximity to extract the contextual information. And then you use it to better solve the given task, the given objective. But these are very abstract examples in the end of the day. So now let's look at another very simple sentence. So the sentence is, the whole class went to the beach after the exam finished. Here we can see a decomposition of this sentence into a parse tree. You can imagine that in order to understand the whole sentence, we humans look at individual words that create this sentence, that make up this sentence, group these words together and merge them to get a new combined information. And we do that because we don't have enough running memory to store information about all these single tokens, about all these single words. We have to combine them to create more high-level representations. And this is enough for us to understand language. So if we don't need this extra memory, maybe the transformer model doesn't need it either. Also, please notice that in this example, tokens are just words. Sometimes our input tokens are characters when we do character level modeling, which make it even more suitable to merge them into words at some point in the model. And yeah, now let's use this intuition to force the model to do that. Let's impose such a prior to our architecture. And yeah, don't worry, I know that a lot is happening on this picture, but I will slowly decompose it into individual layers, which are much easier to comprehend. So what I can say right now about the Hourglass architecture in general is that the whole model is symmetric. Like in EUNet, the first half is a contracting path to capture the context, the high-level information, while the second half is an expanding path that enables precise generation, the optimization of our objective function. Also, please remember, that in case of any questions, I encourage you to ask them straight away. So the first component. In the beginning and in the end, we have standard decoder blocks with attention module and feed-forward block. If we would have removed the things in the middle, the rest is just a stack of decoder blocks, your current implementation of transformer model. And we call them vanilla layers, the layers that operate at the resolution of the input sequence. And these are placed in the beginning and in the end of our model. Then, after pre-processing the input with few vanilla layers, we shorten the input for the first time. To do so, we use shortening layer. And a shortening layer is in fact any function that takes two arguments, a sequence of tokens that is a tensor of shape, length by dimensionality, and K, which is a hyperparameter we call a shorten factor. It indicates how much we want to shorten the sequence. The output of a shortening layer is just a tensor that has K times smaller length. Example of such shortening layers that are implemented in popular frameworks and satisfy these criteria are average pooling or shredded convolution, for example. Then I told you that the model is symmetric. So after shortening, we have to implement symmetric operation that will upsample our sequence back to the granularity from just before shortening. We want that because this will allow us to incorporate the high-level information processed by the blocks in the middle. So these are the blocks that will be operating on the shortened sequence. This sequence that we hope that will contain and work on more high-level features. And the simplest way to upsample the sequence is to repeat each embedding K times. Another example of a valid upsampling layer is deconvolution. Both of these increase the length of the sequence so that this sequence, this upsampled sequence can be easily added to the representation from just before the shortening layer with a residual connection.
What do you mean by deconvolution?
So yeah, I think that so the convolution is kind of a like linear transformation that we can use to upsample one token to many tokens, and that's just a linear transformation, and it's very hard. I find it hard to explain, and I think that the picture tells more than 1,000 words. So it's best to maybe type in Google what's the operational deconvolution. But basically, it's just linear transformation that we can apply to a single token. We apply this position-wise, and we can cast a single token. And with the use of this linear transformation, we can actually, upsample a single token into many tokens by making the dimensionality longer and then splitting into many tokens with the same dimensionality that we started with. Yeah. But yeah, actually just, there are many options to actually upsample the initial sequence, the shortened representations, and deconvolution is just one of the options that you can read further in the literature. So, but we don't have to focus on that. We can also just think of that as a way to upsample the sequence, just as we can upsample the sequence by repeating each embedding a few times.
Well, I guess I did follow your advice and look, and I suppose my guess for what deconvolution would be that you would take the matrix that implements the convolution as a linear operator and then take the pseudo inverse of that. Is that?
Yeah. Okay. Yeah. Yes. So yeah, let's go further. At this point, we can repeat the whole procedure of shortening and upsampling multiple times and in place another hourglass using recursion. And actually, this is it. So this is the high-level overview of the architecture that we propose. And here is one technical detail that I would like to explain more specifically on how to apply the shortening layer so nothing breaks. And the problem here is that in autoregressive models, we cannot leak the information from the future during the generation because we want to rely only on the past. If we leak the future tokens, the task becomes trivial and the model doesn't learn anything because knowing the future, it can just copy the future. And the default transformer decoder solves this by shifting the input sequence to the right, and then by applying causal lower triangular attention mask inside the self-attention module. And it's enough to prevent the model from looking into the future in standard transformer decoder. In case of Hourglass, we merge the subsequent tokens into groups, and then these groups get upsampled again, and they are added to higher resolution representations from just before the shortening. And have a look at the picture right now and see what could possibly go wrong. So here we shifted our initial sequence by 2 to the right and then shortened it by a factor of 3. So we merged each 3 subsequent tokens into a single token into one group. Because of that, the first shortened token have an information about the first target token that we want to predict, the blue one. After upsampling, this information will be incorporated to the first token that was blank before and will be used to perfectly predict the blue token just by copying it. And to prevent such a situation, we do 2 things. At the beginning of the processing the input, we shift the sequence by 1 element to the right because we designed our model to have few vanilla layers in the beginning to pre-process the input before the shortening. So we apply the same procedure as in the standard transformer model. So we shift the sequence by 1 element to the right at the beginning. Then, before each shortening operation, we have to shift the sequence further to the right by shorten factor -1 tokens. And this is the smallest shift that prevents the aforementioned leak at any point in the model. So to sum up, the only thing that is needed is this additional shifting before doing each shortening. And we don't have to care about the upsampling operation because it doesn't change, and by just shifting by this shorten factor -1 tokens, we solve the leak problem and we are good with our autoregressive property.
Can I ask just a trivial question about that picture?
Yeah, of course.
So is the sequence going left to right or right to left?
Left to right.
Left to right. So, okay, so you're shifting the tokens to the future direction.
Yeah.
Okay.
Now a quick recap about the model from a different perspective. Another thing that we postulate in the paper is that the idea of Hourglass is very easy to code. And actually, if you have a working transformer code, you can change it to Hourglass with just a few lines of code in most of the deep learning frameworks like PyTorch or JAX. The only assumption that we make about your current transformer is that your implementation is a stack of standalone transformer blocks. Whatever attention implementation you are currently using, and that could be sparse attention or kernel-based attention, you don't have to change that because the idea of Hourglass, the idea of shortening the sequence, is completely orthogonal to the self-attention blocks themselves. And this pseudocode can actually be transformed to the real Python code that we can see on the right. And now the most interesting part. So actually what follows after this slide. But let's start with theoretical advantages of Hourglass. So let's see how shortening the sequence affects the complexity of a single Hourglass layer. The complexity of attention mechanism from a vanilla transformer is quadratic with respect to the input length. And that's the situation where Hourglass achieves the biggest speedup because the overall complexity is reduced by a factor of k squared. On the other hand, in transformers like Performer that use linear approximation of attention scores, the use of Hourglass reduces the complexity by k. And yeah, like what we can do with that, this space that are created by reducing the complexity of the model. So let's see how by taking some explicit shorten factor. If we follow some basic calculations, we get that having 2 vanilla layers should work approximately as fast as 8 layers operating on a sequence shortened twice, or 18 layers on a sequence shortened by 3. And I expect that right now you're like, yeah, that I'm cheating, and 18 layers instead of 2 layers, it doesn't have right to work. And you're quite right. It's not that good, but very, very, very close. Because the complexity of a transformer block is not only the self-attention, which is quadratic, but also few linear transformations, and we also have the feed-forward block. Both of these are linear with respect to the sequence length. But anyways, it's still amazing, and let me show you some results. What you can see on these graphs are our results on NWiki language modeling benchmark. First, please have a look at the graph on the left, where we plot maximum allocated memory during training against the final perplexity. We decided to compare ourselves with Transformer XL for 2 reasons. Firstly, it's very strong baseline on NWiki in general. Secondly, Hourglass uses Transformer XL with relative attention in default implementation because we found it relatively easy to code. And therefore, the only thing that differs between these 2 models are additional shortening and upsampling layers. The code base is all the same, and it was actually very closely implemented by the pseudocode that I showed on some of the previous slides. And we can see significant improvements over the baseline. On the right-hand side, we see the plot of seconds per 1 training step versus the final perplexity. And the lower, the better. So the lower, the better, because the less we need to do 1 training step, the faster we will complete our training. And please notice that both of these graphs consist of the same models, the same hierarchies. And in both of them, we see improvements. So to conclude, we observe that implementation of Hourglass, the idea of shortening, creates this little space of reducing the complexity that we can use to first create this hierarchy and impose this prior, and also to possibly also to add more parameters, more layers, and that will be very beneficial to the overall performance. So on NWiki generation, Hourglass is not only better in terms of the final perplexity, but it is also faster and uses less memory than Transformer XL. We have also done similar comparison with Reformer, but these results haven't been included in the current version of a paper. Let's jump onto a few ImageNet results. Hourglass sets new state-of-the-art on ImageNet 32 among autoregressive models and scores competitive results on ImageNet 64. I also include on this slide a few examples that show Hourglass performance on a real task. And in this task, we were given only a top half of the image, and Hourglass had to complete the bottom half. That's just some kind of showcase, but I think that the predictions made by Hourglass looks sensible. Last but not least, I want to talk a little bit about how to design your own Hourglass. And the natural questions would be, should we shorten our sequence only once or multiple times? Should we add one more vanilla layer operating on full sequence, or 10 more layers in the middle on sequence shortened 10 times? And we didn't find explicit answer to this question. The hierarchy is just another hyperparameter. We observed that generally it's beneficial to do at least one shortening by a factor of at least 3, while keeping more than 2 or 3 vanilla layers to first pre-process the sequence and then to post-process the sequence with after incorporating this high-level information that was processed in the middle. And finally, I want to talk about the scaling laws of transformers. So we all have heard that if you have a big data set, then the bigger the model, the better the results. We wanted to compare various hierarchies of Hourglass with transformer XL baseline to make sure that scaling laws hold. And on the right, we can see that the slope of a line fitted to the points representing Hourglass and transformer XL model is almost the same for both models. So we can assume that these scaling laws of transformers still hold even though we shorten the sequence in the middle. Finally, I want to tell you about a little trick that we didn't mention in the picture, but in the paper, but that could be very beneficial to the evaluation of this language model during inference time. So first, look at the sample model in the top part of the slide. We have 3 vanilla layers in the beginning and in the end. In the middle, we have we shortened the sequence once by a factor of 3, and we have 24 layers operating on this shortened representation. In fact, this is our ImageNet state-of-the-art config. If you look closely at what tokens enter the shortened subnetwork, then you can notice that the evaluation in this subnetwork in the middle changes every 3 steps. We see that for the first 3 steps, we do processing in the middle subnetwork on 3 blank tokens that got merged into one single blank token. Then, after 3 steps, we have 3 new tokens predicted, and these 3 newly predicted tokens get merged into a new single token that gets appended to the representation that enters our shortened subnetwork. And again, this evaluation is new for one step, but it doesn't change for the next 2 following steps. And as a result, we observe that we don't need to run this subnetwork at every time step during inference, but only once every 3 steps in this case. But that's just a technical trick and possible benefit that you can take from Hourglass. Here I'll start my final slide and take my takeaway message. So to conclude, we don't need to operate on original granularity of the sequence throughout the whole layer stack of transformer model. Secondly, I encourage you to impose hierarchical structure to process the input and use these savings to have more parameters. more layers in general. And finally, once again, hierarchical transformers are better language models, and and I hope that I proved that a little bit. And thank you. It was a great pleasure to have an opportunity to talk to you about our work today.
Thank you, Piotr. Interesting talk. If there are questions, I'll take questions. I have some questions, but just to, again, some of the details which maybe the experts are familiar. So what was the width of the transformer X to baseline, and what was the minimal width at the narrowest point of your better model, that say the one with the most parameters?
Sorry, can you repeat the question?
With being a number of words, that the attention can look at simultaneously. So,
okay, so basically we did experiments on NWiki generation, and we used the sequence length of 2000 of 2K, and then we show in the paper results where we shorten the sequence multiple times, and like for the input of 2K, the lowest length of a sequence that gets shortened it was shortened by a factor of 12, something like that, or something in between 12 or 15 or 20. That's that range. But we have also evaluated this model on ImageNet 64 that is length of 11K, something like that. And we, in our state-of-the-art result, we shortened the sequence by a factor of 3. But again, the hierarchy is just a hyperparameter, so that we found that multiple hierarchies work the same and produce the same results.
Okay. I mean,
and of course, sorry, I will interrupt. Just to finish, I will add that so we were kind of restricted by the maximum length that we can input, of course, by the virtual memory on our graphic cards. But this can be addressed by using different attention implementations, like sparse approximations of linear approximations for example, in Performer. So you can combine the shortening the sequence with using the attention blocks from Performers. So you're actually as restricted on sequence length as the Performer is, for example.
Okay. Did you consider letting the shortening mechanism have learnable parameters? I took it from your description that you took a fixed max or convolution, but you can imagine the shortening mechanism also having parameters.
Yeah, of course. And yeah, that's the question that actually excites us the most right now. And we are doing a lot of further work on trying to come up with a shortening mechanism that is dynamic. So it will account for dynamic nature of words or some objects in images. So words, of course, can consist of different number of letters, and it escalates even further when we talk about paragraphs or just big parts of papers. So yeah, so we are working on dynamic shortening mechanism that will use some. Right now, we are thinking about the boundary detector gate that will work with the combination of recursive neural network, and we are trying to work on that, but it's still the work in progress. So right now, we are aware that we have this prior that we merge these tokens into fixed size groups, but we are trying to address that right now in further research.
Okay. More questions from the audience?
I have a question. So you've used this for language modeling, which seems like one of the standard approaches of transformers, but you can also use it for just like a classification task like ImageNet. And then I imagine you wouldn't actually have to do like the UNet architecture. You could just stop at the smaller layers, right? Like a convolution does, where it just keeps going down. Have you looked into that? Like, I imagine you might be able to do like pixel-wise, like ImageNet pixel-wise now, if you wouldn't have to like lump it into patches.
Mm-hmm.
Because this would effectively patch it itself.
Yeah, like with dynamic pooling probably. So that's why we are so excited about the dynamic pooling idea. But answering like the most critical part of your question is that so here in this work we worked on the autoregressive model that will be applicable to language modeling or for image generation pixel-wise, and we actually built on the work of full transformer, and that's what you're talking about. So there are some preceding work that actually does that, and the encoder part is a little bit easier, just as you said, because we can, for example, stop in the middle. We doesn't have to upsample the sequence. We just can extract one representation that will contain the whole contextual representation of our input and can be used for classification or some other tasks. But that's the role of funnel transformer. So you can take a look at that.
Thanks.
More questions?
Yeah, I had a question. In your model, there were some dotted lines going from the downsampling to the upsampling setting. So there's some information flowing that doesn't go through the hourglass path, or can you explain a bit more about what the meaning was of the dotted lines?
Yeah, of course. So that's the idea taken from the neural architecture ResNet. So that's like the residual connection that okay, so what we find critical for good performance of this model is that we include these vanilla layers, so that operate on the full granularity on the original granularity of our sequence. And we use vanilla layers to first pre-process the sequence, and in the end, pre-process the sequence to like get them prepared for shortening operation. And we use them in the end to better optimize the objective. That is, for example, pixel-wise image generation or letter by letter some language modeling. So we want to, okay. So at first, when our sequence is its original granularity, by shortening, we don't want to lose that information that we may find critical in then optimizing the objective. We want to shorten the sequence to encourage it to think in more high-level terms, to lose some information that it may find in the end critical to optimize this hard objective, just like I started. So in ImageGPT, they observed that the model first learns the high level. It first starts to look at the local proximity of tokens. It gets the contextual representation, but in the end, these representations are very specific. These representations aren't good for downstream tasks, because they are actually at the state to optimize this very specific objective. So to sum up, we don't want to lose all of the information. We want to lose some of the information and to encourage the model to think in more high-level terms, and then incorporate this high-level information to better optimize very specific objective, which could be language modeling.
Thank you. That's very interesting.
At
Yeah,
the level of code, the dotted lines are residual connections. Is that fair? Is that correct?
Yeah, correct.
Okay.
How does it combine the residual inputs with the Hourglass inputs? Does it concatenate the vectors? Does it add? How does it come up?
So again, it's again like a hyperparameter of architecture. We just add the representations and find it like 0.1% better, but it's just like overfitting for a task. So you can basically add or concatenate and expect very similar results.
Okay, you tried them both, and the results are similar.
Yeah, exactly. So in the end, we just add because it's a little bit simpler.
Right. Okay, yeah, no, I mean, it seems like a very crucial point that, I mean, for example, when you said that you could do the, operate on the larger granularity, I was very confused, but now I see because of the residual connection, you can still predict the original granularity, yes.
Yeah.
Okay. More questions?
I have a question just about is there, would you say that this is just a superior architecture to transformer, or are there downsides to it? I mean, obviously there's hyperparameters where, it's hard to say what's equivalent to replacing a transformer with this, but do you think that overall it just performs better on language modeling tasks, or?
Yes, I believe so. So what we are stating, what I believe is happening here is that we are creating this space by reducing the sequence length, the complexity part, but also the memory that we need during training, and we can use it to have more parameters. And this part is unexplainable, I think, for anyone. So why having more parameters creates better models, but it's just the way it works. So yeah, I think that in general it works better because we found this space. We found this space that we can use to have more parameters under the same settings, and it's just a different axis to optimize our transformers, I think.
Here's a thing that might be interesting to try, would be to take one of the big highly trained models, the GPTs, and the big models of the big labs, and take one of those, but then use it as the residual, and then train one of these Hourglass things, next to it, and add those, so that you could gain something from both.
Yeah, of course, but you need to, if I correctly understand what you're talking about, then you need resources to train these big models.
So the big model, clearly you need huge, huge computational resources to train the model, but you don't need huge computational resources to train your model. But you could try combining, the pre-trained GPT with this.
So how I think about that is that you actually should rather use like Hourglass for this pre-training objective that is currently used in GPT-3. So I'd rather see it to train GPT-4 using the idea of Hourglass, and under the same settings, like the computational settings, it will be more effective. And that's
No,
what
not
I would-
that, if you have the computational power to do it, yes.
Yeah.
Okay. More questions or?
Can I ask
Okay, well,
another one?
please, is there?
So I've been talking about pre-training. Like, I guess you're adding more layers, but the layers that are basically the same shape as like the original transformer layer, right? So
Yeah.
like, could you take, at least for some of the layers, like take pre-trained layers and then train on top? Like, well,
yeah.
okay, maybe this is silly because eventually, if this is a good model, someone will just pre-train on this. But like, as kind of a stopgap, like, could you take a transformer of the usual shape that's pre-trained on something and then shove this in? Obviously, it wouldn't like remember English probably because you're changing everything around, but it would have like
Yeah. I see the point.
computational.
I see the point. So, yeah, probably, probably like from like deep learning and optimization of this function is magical. So it probably could learn something sensible. So yeah, you can take like GPT-3. You can split the model in half and put some layers in between, and fine tune for like few steps, possibly needing less resources. Again, so fine tuning these extremely big models like GPT-3. Okay, it wouldn't be possible that like straight off the way, but the work of Reformer from like 2 years ago, I think, provides some very interesting idea how to save memory in transformer models. So you can train really, really big models under very small setup and under very small available memory. And I also encourage you to have a look at this because we also used Reformer in some of our experiments here in Hourglass. And with Reformer idea, we could train like 200 layers Hourglass efficiently.
More questions? If not, well, let's thank Piotr for a very interesting, exciting talk. Next week, we'll have, let me look up the name, Untitled to speak about quantum, basically complexity theory of quantum approximation of Hamiltonians. So I look forward to seeing you all there, and thanks for attending. Thanks, Piotr.
Thank you very much. It was a great pleasure.
Okay. Stop the recording.